Okay, so today is recitation 3 slides, and we are going to go over some of the scatter plots, okay? Some of the scatter plots concept and some of the correlation concept. So discuss exploratory data analysis and develop a better understanding of what correlation is, how to interpret it, and deal with some examples. Um, so we talked about histograms and bar plots in the last recitation session. So uh, they all fall under exploratory data analysis. As the name suggests, what you're doing is you are looking at your data, seeing its shape, seeing what sort of a distribution it might have, seeing if it has any outliers or not. So when you plot it, it's very easy to see it, right? So those kind of plotting and those sort of things, we do fall under the topic of exploratory data analysis. So it depends on what kind of a variable you have, right? So if you have a categorical variable, think of subjects and think of a yes or no question. Let's say we have 100 subjects and you have responses like yes, no, yes, no, yes, no. Then you can visualize this. So this is a categorical variable, right? So you have two categories. It's a nominal categorical. It does not have any natural order to it. So you can do exploratory data analysis to this as well. You can draw a bar plot. A bar plot for this will look like something like this. So hello, where's that? Yes, please come in. It's a hybrid session, so I'm doing it over Zoom as well. Yeah, but you feel free to join. So we are talking about like different kinds of variables and how to plot them. Okay, so this example is for a data set like this, where you have like 100 subjects, and you're asking each of these subject a yes or no question. And this variable is a categorical variable. So there are two categories, yes and no. So what you can do is you can plot it like this, and this is called a bar plot. What you're simply doing is you're visualizing your data set. It's easy to see that the number of yeses is much larger than the number of no's, right? So there's 70 people who said yes, and there are 30 people who said no. So this is one of the ways how you can visualize a categorical data set. With bar plots, you can also do pie charts, right? So you could have a pie chart, say, and then, based on the percentage, if percentage of yes is 70 out of 100, percentage of people who said no is 30 out of 100. So you can plot it like this, where this is the people who said yes, and these are the people who said no, right? So these both of these bar plots and pie chart are a way of visualizing your data set, right? It's when you look at it, your data set like this, it gives you a clear picture. Then looking at things like this, which is in a very raw form. Okay, so so this was for the categorical data set. For numerical data set, you have a bunch of options. You can do a histogram, a scatter plot, or a box plot. So when you do these three kinds of plots, what um, what you can see is what kind of a distribution your data set has, if there are any outliers or not, and stuff like that. For example, I'll give one small example. So, so imagine a numerical data set now. So we worked with categorical before. Now, so let's say you have 100 subjects again, and now the variable is a numerical variable, say height, right? So for each subject, you ask the height of that subject. So 5.5, height in feet, 5.6, 4.0, something like that. So you have a data set like this. So what you can do is you can plot a histogram like this, where each of these are 4 to 5 feet. Let's say let me change it. Okay. So what I'm doing is I have that data set and I want to visualize it. And let's say the data looks like this. This is 5.5 to 6, 5 to 5.5, 4.5 to 5, 4 to 4.5, and 3.5 to 4. So drawing is not clear, but so I'm increasing by zero point 0.5 in feet. Okay. So what do you understand from this histogram? Sorry, let me draw it a little more nicely. So it's 4.5 to 5, 5 to 5.5, 5.5 to 6, 6 to 6.5. So let's say there are 20 people who are in the range of 4.5 to 5. There are 30, there are 40, and there are 60. Okay. So is this clear what I'm trying to do here? I'm just trying to see this data set in a more organized way, and then I plotted a histogram. And this is what I see. I see that 20 people are in the range of 4.5 to 5. Uh, more people are in the range of 5.5 to 5, 5.5 to 6, and 6.6 to 5. So what kind of a distribution is this? It's left skewed distribution, right? So uh, it's a distribution like this. Um, so that is one of the things you can also do from your histogram, is to see what sort of a distribution your raw data set, this is your raw data set has. And this is a left skewed distribution, meaning there are more observations, there are more people who are taller in this data set. Yes. Yeah, you cannot tell from the raw data because this is what you see from the raw data, right? So you see for each subject you see a number. So that's why plotting is useful. Yeah. When you plot histograms and box plots and scatter plots, it tells you about the shape of your data set. It tells you about the 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 direction in which it is skewed. It tells you about the outliers that might be the data set. So you might have, you might get a histo for a different data set. You might get a histogram like this, right? And then if I ask you what is the shape, then you say it's a normal shape. It's a symmetric belt-shaped distribution. Okay. Um, And yeah, and it probably has no outliers. So yeah, yeah, outliers are so let me add you. So outliers are data points that are far away from what normally you see. For example, take this data, say one, um, two, three, four, five. Let's say this is the number of children that somebody has, a family. You go and ask a family how many children they have. So you ask, let's say, six people. Okay, so these are the answers you're getting. And for the sixth, they have 10 children. Okay, so this 10 will be an outlier for this data set because most of your data is something like this: one, two, three, four, five. It's in a community, and this 10 is a different, does not follow what your data is suggesting. So this will be a possible outlier. Um, the thing is, you know, I was talking about this in the last class, last recitation as well, but there is a measure of center. And there is a measure of spread. Okay. So whenever you see a data set, whenever you see a distribution, it's important that you know where the center is and what is the spread of that data set. Okay, so these three things will tell you where the center of the data set is located when you find a mean, median, mode, right? So, and these three things will tell you how far are your observations in general from the center. What is your spread, right? So, for example, uh, let's say height. So this second histogram is more spread out, right, than the first one. So the first one has a lower measure of lower standard deviation um, because it's not spread as much. Okay, the second one has a higher standard deviation because it's spread. The measure of center is the same. So the center is the same for both data set, uh, but the spread is different. Okay, so you will have different combinations of things. And you cannot always pick any out of the three. Okay, so it depends on whether your data set has outliers or not. If your data set has outliers, then mean, uh, so let me write it here. So if no outliers, right, you can choose mean and standard deviation to explain the center and spread. If there are no outliers in a data set, you can calculate this and you can calculate this and you can say this is my measure of center, mean, and this is my measure of spread, standard deviation. But when you have outliers like this in your data set, you cannot use mean and standard deviation anymore. Okay, they are they are sensitive to outliers. So in such cases, if outliers are present, use median, and interquartile range. So you use median and interquartile range instead of mean and standard deviation. Okay, does that make sense? So if somebody gives you a data set like this and tells you what is the measure of center and what is the measure of spread. Somebody gives you a data set like this, tells you the measure of center and spread. First, what you need to do is plot the histogram, see what sort of a distribution it is, see if it has outliers or not, and based on that, you select the appropriate thing out of this. Okay. For this one, possibly, possibly. But I mean, based on, so this is a very raw kind of a picture. Okay, so you need like actual plots. But what I mean by that is here. So when you have a symmetric distribution, um, when you have a symmetric distribution, all the measure of center, mean, median, and mode, they are at the center. Okay. Remember, mean, median, and mode are the measure of center. It tells you where the center of your data set is, right? So when you have symmetricity, when you have a data set whose histogram is like this, then the mean, mode, and median are the same, exactly same, and they are at the center right here. Okay. When you have a data set like this, which is right skewed, so this is right skewed. It has a tail towards the right, so it's right skewed. This is left skewed. Now the measure of center is not the same. Okay, the three things they change. They are not at the center anymore. The mean the mean changes. Right, look at the mean. The mean is sort of being pulled in the direction of the tail. Right. The mode is always easy to identify in histograms as it is the tallest bin. Notice how the mean is affected by the skewness. The skewness pulls the mean in the direction of the skewness. Okay. Is this clear? What I'm doing here? So one example of this would be this. So let me just like a raw example. Consider the same data set. 1, 2, 3, 4, 5, and then 100. Okay. What is an outlier here? 100, right? Now, if I tell you what is the measure of center here, what would you say? So what are the three measure of center? True, but let's find all the measure of centers. What is the mode of this data set? They all show up equally, right? So there's no mode. Mode means the number of values that are repeated, right? So there are no mode. What is the mean? Can somebody calculate the mean? So you just sum up all the numbers and divide by the total number of numbers, right? Which is 6. 31.6, okay. And the median? How do you find the median? Median is the middle value when you order your data set in an ascending order, right? Something like this. So this is already ordered. So what is that value that divides the data set into two halves? 3.5, right? So this here is the split, right? So So now if I ask you, what is a good measure of center? What is it? Is mean a good measure of center? Why is mean not a good measure of center? True, right? You can see that 31.6 is let me write the data set again. 31.6 is somewhere here, right? Is this the center of the data set? No, right? This is not the center of the data set. So mean does a very poor job when you have an outlier. Okay. Whereas the median is not so much affected by it. Okay. The median is 3.5, which is here. And this is a good measure of center. Okay. Uh, so does that make sense? Yeah, right. So if you take a symmetric data set, so what is the what in terms of histograms, where is it skewed? Left skewed or right skewed? This data set is left skewed or right skewed? Right skewed, right? Because the outlier is 100, so it's something like this. Now, if the data was like this, negative 100, 1, 2, 3, 4, 5, then it'll be left skewed, right? Now, if the data was symmetric, and this is a very simple example, okay? So uh, just to make you understand how mean is affected and why you cannot use it when you have an outlier. So what is the mean here? So there is no mode, right? There is no mode. What is the mean of this data set? 3. Is this true? Right? When you add all the numbers and divide by 5, you get 6, 10, 15, 15 divided by 5, 3. Median is 3. So now you can use the mean and the median as a measure of center. Mean is not affected. Why? Why is the mean not affected here in this case? No outliers, right? I removed this 100 outlier. Now this data is pretty symmetric. And now you can use mean, median does not matter. Okay. So that's what's happening here. If it is symmetric, you can use mean, mode, median. It's at the center. Any measure of center is fine. When you have an outlier uh, in in a right direction, like we had with this 100, right? The 100 is probably somewhere here, and your 1, 2, 3, 4, 5 is here, right? So your mean shifts towards the 100, right? Your mean is very much affected by the outlier. Same case. If you have negative 100 and then have like 5, 4, 3, or like 1, 2, 3, 4, 5, then your mean is shifted in the direction of where your outlier is. So mean is no longer a good measure of center. It does not tell you where the center of a data set is. Where your median becomes a good measure of center. Okay. Let me see if there are any chats. No chat. Okay, no chat. So now let me talk about scattered plots. Okay, so scatter plots are another exploratory data. So what all of the things I'm talking about fall under exploratory data analysis. Okay, you have a data set, you want to visualize it. Histograms we talked about, box plots we talked about in the last recitation. So today is scatter plots. Scatter plots are just the plots between two variables. Okay, so here you see that um, as age is increasing, what is happening to the salary? So let me make it big. So as the age is increasing, when you're 20, right, your salary is not that high, right? When you are 25, then it, your salary, there are people with very low salary, there are also people with very high salary, right? And when you are, let's say, 35, same goes. The people with very low salary, very high salary. When you're 40, it's usually a low salary, probably, I don't know why. But this is what scatter plot does. Okay, you have two variables, you have age and you have salary. You plot them against each other and you see as one is changing, as age is changing, how does the salary change? Okay. Scatter plot uses dot to represent value for two different numeric variables on a graph. We use plots like this to study the relationship between them. Okay. Um, yeah, we see if there's any pattern or not. If when age is increasing, is salary increasing for sure? So to see pattern, to see connections between two things, you draw a scatter plot like this. Okay, so that's the main idea of scatter plot. Why do you draw histograms? To see the shape of the data set. Okay, and this is for a single variable, right? If you collect, if you collect height, if this is one variable, then you have the histogram of height, right? But what if you had height and so let's say you had now you not only had height but also had weight of those subjects, right? Let me take 100 subjects, height and their weight, 100 pounds, or let's say let me make it 150, and 5.6, 100, maybe 60, something like this. You ask 100 people for their height and also their weight. Now you guys understand the histogram is for a single variable, right? It's for one variable. You see what is the distribution of the height variable, what is the distribution of the weight variable. Now what scatter plot is doing is taking these two variables and plotting them together. Okay, so let's say this is the height and this is the weight, and you see plots like this that helps you see the relationship between the two variables. Is that clear? Yeah. Yeah. um so was I okay? Now the thing is, what if let's talk about the height and weight example. So let's say this is height, this is weight, and you see a trend like this. um let me take a different example, okay, so it's clear too. Let's say I do something like this. I have subjects, I ask their grade or GPA. Then I ask students number of hours left, um, time spent at Nodegate. So I ask all of these questions, okay, for 100 subject. You can, let's say for first subject, the GPA is 3.3, the number of hours they sleep every day. Okay, every day is let me make it 3 points. Let me make it a bad student. Okay, so number of hours slept um is 6, or let me make it 5.5, and the number of every week is 15, 15 hours. Okay, right. So you collect data set like this, and at the end, what you do is you plot a scatter plot between the GPA and uh, number of hours slept. And let's say uh, you see a plot like this. Okay. Now, what can you infer from this plot? Yeah, so what does it look like? It looks like as the numbers of hours slept is increasing, as people sleep more hours, their GPA tend to increase, right? At least that what it is telling it from this data set. Uh, so what kind of a relationship do we see between the two variables? A positive relationship, like you said, right? When one is increasing, the other is also increasing. So what kind of a relationship will this be? Something like this. If you say you have variable 1 here, variable 2, negative relationship, right? And what kind of a relationship will that be? This will be no linear relationship, right? So as you know, as this variable is increasing or changing, variable 2 does not change. So now comes the important part. Okay, what can I say that, so based on this plot, can I say that uh, sleeping more hours causes your GPA to go up? Can I make that statement? Why not? It's true. So you guys have studied those kind of things, right? So I cannot make a conclusive statement about causation. Okay, what I mean by that is I cannot say that the more hours you sleep will cause your GPA to go up. So that's a very strong statement, right? So what we see is some kind of an association between the two variables. Okay, we see that as number of hours slept is increasing, your GPA is going up, but that does not mean sleeping causes GPA to go up. Okay, it's one of the variables that might come into play, but there might be other variables as well. So you have to be careful about how you, when you see a scatter plot, what kind of a statement you can say. Okay, you cannot say statements with causation. You cannot say this causes this just based on the scatter plot. It's not enough evidence. Okay, just because the two variables are correlated does not mean one causes the other to occur. Okay, correlations alone don't show us whether or not the data are moving together because one variable causes the other. A strong correlation might indicate causality, but to prove it, it requires much more testing. Okay, so it might be the case that sleeping causes GP to go up. This is a strong evidence. Okay, this is sort of leaning towards that, but we cannot just based on this make that statement. Okay, so there is a so this is very famous in statistics. I think you'll be tested for this in the exams as well. Is when can you say correlation things and when can you say causation things? Okay. Um, any questions about this? All right. Yeah, same thing, right? So look at this, right? So so salary is your so they have names, okay? So this is called explanatory the variable that you plot on the bottom or on the x-axis is called an explanatory variable. This is called a response variable. Why explanatory? Because this salary is explaining the car price. Okay, it's how when there are changes in salary, the car price is changing. So this is an explanatory variable, and this is a response variable. It's changing as salary is changing. Okay, so these are the two names for it. Um, what if let's say what I collect subjects. What can I collect? Um, walking speed and heart rate. For 100 subjects, I collect this data set. Okay, whenever they go on a walk, what speed they walk in, and what is their heart rate. Okay, now what will go on if you draw a scatter plot for these two variables, seeing if they are related or not? What will go on the x-axis? What is the explanatory variable, and what is the response variable? So you're saying walking speed goes here, and heart rate goes here, right? Why is that? True, 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 right? It's what you're interested in seeing, how when walking speed changes, how does the heart rate is responding, right? That makes much more sense. Whereas having when heart rate changes, how does walking speed changes does not make really much sense. So 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 you have questions when you're given two variables. You have to first identify which one is the explanatory, which one is the response, and then go about other questions like causation and correlation. Okay, does it make sense to you? Yeah. Uh, Whatever is being explained will be on the y-axis. So this is the y-axis. This is the x. It's a two-dimensional data set, right? So um, what will be another example? Yeah. So here, this makes much more sense, right? As salary is changing, how is the car price being affected? Uh, So car price is the response, and salary is the explanatory variable. Now, so what sort of a relationship do you see between these two variables? A, a positive correlation, right? So as you are earning more salary, it seems like the the car price or the price of the car you own is also increasing. So you're buying more and more expensive cars. Um, However, you cannot say more money makes or causes you to have a more expensive car. Okay, so you can say there is a positive relationship. We see a positive linear relationship between these two variables, but that's you are stating correlation. You're saying these two variables are correlated. Okay, but you cannot make this statement. You cannot say this variable causes the other to go up or down. For example, some kids make no money but drive nice cars because their parents bought it for them. You know, also some people who make a lot of money might choose to spend that money elsewhere and not drive a supercar. Yeah, yeah. So another plot. So it's a sort of a negative relationship, right? The more wine you consume, your heart disease deaths seems to go down. But you cannot just based on if you are a doctor based on this plot. Oh, the heart disease death are going down, so I'm a prescribe more wine to my patients is not a good idea. So you cannot make, again, causation statements. From a scatter plot, what you need to see is the trend. What direction is it? Is it linear? Is it not linear? Is it, if it is linear, is it positive or in a negative direction? And what is the strength of the linear relationship? Okay, and then if there are any outliers present or not. So let's go to this. So this is positive linear, right? It's a linear relationship and it's in the positive direction. This is negative linear. This has no relationship, no linear relationship, right? It's all over the place. It's, you cannot do this, you cannot do this. This. As this variable is changing, you cannot say this, how this variable is changing, right? It's all over the place. This is changing like this. As this variable is changing, this variable is increasing at first and then decreasing, right? And this changes like this. So out of these five plots, how many show linear relationships? 2, right? And what about D and E? If I ask you the question, this specific question, okay, is there any relationship between the two variables for D and E? What will be your answer? Yes or no? Again, is there any relationship between the two variables based on D and based on E? And you have two options, yes and no. So you're saying there is a relationship. Okay. Why is that? Yeah, you're thinking in the right direction. So my question is this: are or is there any relationship between the two variables? And I give you this plot. And I also give you this plot. Let's say I just give you this plot. And what would you say? Yes, no. Yeah. Yeah, yeah. So your answer will be yes. And your answer will be also yes. Right? So yeah, that is true. There is a relationship. It's called a curvy linear relationship. Uh, and there is also a relationship, but there's no linear relationship. Okay, so that's very important to identify. Linear relationships are here on the first two. What do I mean by linear is it's increasing in a linear fashion. Okay, uh, like the first two plots. Whereas D and E, it's not increasing or decreasing in a linear fashion. It has some relationship. You cannot say there is no relationship. There is some relationship, but it's not linear. Okay, so that's important because in exams you can see trick questions like that. Right? So I ask you, is there any relationship? Then you'll probably who think of probably people will only think of linear relationship and say no, right? But there is a relationship. Now, if I ask you, is there any linear relationship in D&E? Your answer will be no. No linear relationships. Again, same thing. Positive direction, negative linear, and no direction. These things are not so much important. Now let's talk about the strength of the linear relationship. Okay, let's say so between these two plot 1 and plot 2, which has a stronger stronger linear relationship. Plot one, right? You can see, right? Because as this explanatory variable is changing, your response is not changing that much. It's linear, still linear, but not as much as plot one is. Okay, so here comes the strength. Okay, even you can have two plots that have a linear relationship, but their strengths might be different. Okay, and that strength is explained by this something called as R, which is called the correlation coefficient. Okay, um, it's called the Pearson's um, coefficient, correlation coefficient. Does not matter, um, but what does this R? So forget about the formula. Okay, what does this R tell you? Is R is always a number from -1 and 1. Okay, so your R is can be anywhere here. This means a perfect negative relationship, and this means a perfect positive uh, linear relationship. Okay, and if it is 0 means no relationship. Okay, so your R can have values between -1 all the way up to +1. Okay, so you see the R is 0.4, right? For this, it's not perfect one. It's not a perfectly linear relationship, but it's 0.4. So it's somewhere here in terms of strength of the relationship. Okay, 0.4. If it was 1, then it'll mean a very perfect positive linear relationship. If it was -1, then it will mean a very perfect negative linear relationship. R is 0 here, means no correlation, right? And when R is -0.4, it means there is a negative correlation, but it's not perfect. Yeah. So yeah, I mean you don't really need to use this formula. This is how you calculate the R. But what you need to know is these things, okay? That R goes from -1 to 1. What does -1 mean? What does 1 mean? If I give you a different plots like this, can you tell me which R corresponds to which plot? Right? So those are the kind of things you need to know. So R measures the strength of only the linear relationship. Okay, R does not tell you uh, yeah. So let's so this is all positive linear, this is all negative linear. Okay, R is probably 0 here. R is probably like 0.4, maybe 0.7 here, and R is 1 here, right? So you see how R is changing, right? um, the stronger R is, the more the strength of the linear relationship. Yeah, and you can see same thing. R is 0 here, -0.4, -0.7, maybe. Okay, and this will be perfect -1. Yeah, so R is always from 1 to 1. I was going to say something else. Yes. So what is R for D and E? Yeah, but what do you think R would be as a safe guess? So what does R tell you again? That was my main question. What does R tells you? How strong how strong a relationship it is between two variables. But does it tell you about any kind of a relationship? only for linear relationship, right? So if I ask you what is R for D and E, you will say that it's probably close to 0, right? Because D and E are not, they don't have linear relationships with them. So R only explains um, only the linear relationship. So that's another like sort of thing to keep in mind. Might have trick questions that test you. Okay, um, R is always between -1 and 1. At -1 and 1, there is a perfect straight line relationship, perfect negative, perfect positive. Uh, the closer to -1 to 1, the stronger the relationship in both directions, negative and positive. The closer to 0, the weaker the relationship. Yeah, if R is negative, then you have a negative relationship. R is positive, it's positive. Okay, so again, you can see R is 1, R is -1, R is 0.4 for this. Positive, but not that positive, but not that strong. Now this is much more stronger, right? And this again is 0. So, and many other examples of this. The last thing I want to talk about is this. Let's say you plot the scatter plot. Okay, let's say for example 1, you have salary and you have productivity, and you see a positive linear relationship. Now, can you can you say this? Is this a good thing to say? No, right? Why not? True. And why do you think this statement is hinting towards causality? True, right? Okay, so this is, yeah, so you guys get it, right? So this is not a good statement based on this. What about the second one? Yeah, yeah. So you tend to be more productive. You're not sure. Looks like it, right? So again, another testing questions in exams, right? So you have to be careful. What about the second? Which one? Which example two? Which one of the two is correct, or it makes more sense? The second one, right? So this is bad. This is good. What about the third one? The second one. So again, the hint is like, when you see more likely words like, you know tend, and that does not say for sure, but gives you a good hint. Um, these are all the bad, good, bad, good, bad, good. So they're ordered like this. Okay.